Okay, let's get started here. It's my great pleasure to introduce T.B. Shardle, who's going to be giving today's guest lecture. T.B. is a research scientist in my research group at MIT, and he has lectured the entire class before, and he's not lecturing it this term. For that, we have Professor Reagan Kelly, but Dr. Shardle is notable for having built the parallelism into the compiler that you're using this term. And he is the chief architect of OpenSilk. And so nothing goes into OpenSilk without his blessing. And he is a phenomenal performance engineer, as well as a compiler expert, as well as has expertise in theory and algorithms. And he can recite pi to how many digits?
On a good day or on a bad day? No.
What's the most you were ever able to recite it in an quote official setting?
In an official setting, it was somewhere over 700.
700 digits of pi. So that alone could get somebody into MIT, right? Without further ado, TB is going to tell us about how your code in C makes its way down to assembly language and how you can look at that and better understand what the compiler is doing to improve your code. So, TB, you're all yours.
All right. Thank you for the very kind introduction, Charles. Hi, everybody. I am today I want to give you a lecture. Oh, let me refocus on the slides. Yeah. So today I'll be giving this guest lecture on how C code gets translated into assembly. And just to put us into the context of where things stand right now, previously in the last lecture, you had an introduction into computer architecture. And during that introduction, you saw some of the basics of the x86-64 assembly language, including the instruction set, the various registers, the different data types in assembly, the various addressing modes for addressing memory, condition codes, the RFLAGS register, and so on and so forth. And so you're looking at files kind of like what was shown on the right, or code that like what was shown on the right. And today, our goal is to connect up this assembly code to the C code that you are writing in your homeworks and your projects. And so we're going to look at how that C code actually gets turned into assembly language, focusing on x86-64 assembly. Now, from previous lectures, you might remember two key things about this process. First of all, that to translate C code into assembly, one of the key tools involved is known as a compiler. And in this class, you're using the Clang compiler, also known as the LLVM compiler. And the idea is you hand the C code to the compiler, and from that, you can get assembly code, especially if you just pass the right flags to get human readable assembly. Now, the other thing that you might remember, specifically from the last lecture, is that there is a lot going on in x86-64 assembly. There is a very large instruction set. There are a bunch of different registers, although still a finite set of registers. Those registers alias each other in these funny ways that you have to keep track of. The data types turn into these suffixes on the opcodes. There are a whole bunch of memory addressing modes, including that base index scale displacement behemoth. This RFLAGS register has some invisible effects when you're looking at comparisons and jumps and that sort of thing. And so from these two key features, the compiler and everything that's in the assembly language, you might be able to guess that this compiler has to do a lot of stuff in order to translate C code into assembly. It has to choose what assembly instructions it's going to use to implement different operations in C. It has to figure out how to implement C conditionals and loops just using conditional and unconditional branch instructions. It has to decide how to allocate registers and memory locations to store the data of the program. And occasionally we'll have to move data among those registers and among locations in memory in order to satisfy various dependencies. It has to figure out how to coordinate all of the function calls in the program, including function calls to functions in other source files. And these days we expect our compilers to generate fast code. They have to work pretty hard in order to make sure that that assembly is efficient. And because the compiler has to do all of this stuff, if we just take a look at some C code, even relatively simple C code, and the assembly that corresponds to that C code that the compiler generates, the mapping between the pieces of C code and the different components of assembly code isn't always that obvious. This is a really simple C program. And even here, the mapping of lines of C code is fairly unclear just right off the bat. So how are we going to tackle this problem? How are we going to understand how C gets translated into assembly? Well, in this lecture, we're actually going to take a cue from the compiler itself, because the compiler itself doesn't do this whole translation process in one step. Instead, it handles the process of translating C into assembly through a sequence of steps. And that sequence of steps is illustrated at a high level on this slide. So we start off with some C source code, and that gets pre-processed by Clang in order to handle all the sharp directives within the code, giving us a pre-processed source. That pre-processed source then goes through a code generation phase, which translates the C code into an intermediate representation, which in the case of Clang and LLVM is known as LLVM IR, IR being short for intermediate representation. The compiler will then do analysis and optimization on that IR to try to make it faster. And then that IR goes through a second code generation phase in which the IR gets translated into assembly language. Now for today, we just want to understand how C gets turned into assembly. And so we're really just going to focus on these two code generation steps. How does C get transformed into LLVM IR? And then how does LLVM IR get transformed into assembly? And so really a better title for this lecture is C to LLVM IR to assembly. Now, just like you can view the assembly code produced by the compiler, it turns out that you can ask Clang to print out the LLVM IR for any given snippet of C code if you just pass the right flags. So previously you saw that you can pass the -S flag to Clang to get the human readable assembly for some C code. If you instead pass -S -emit LLVM, you'll get LLVM IR code, as shown on the slide. Similarly, if you have some LLVM IR code, you can turn that into assembly code, again by invoking Clang with the right set of flags. And it's in fact the same flag that we'd use to transform C code into assembly. And so today I want to overview what is this intermediate representation, what is LLVM IR, and then how do various constructs in C get translated into LLVM IR, everything from straight line code to conditionals to loops and so on. We'll then take a look at the other end of the process for how LLVM IR gets translated into assembly, and that'll bring us primarily on the topic of the Linux x86-64 calling convention. And then at the very end, I want to wrap it all, tie it all together by looking at a simple case study where we look at a single simple C function and how that gets transformed through this entire process. Now, as Charles mentioned before, I have given lectures in 6172 a couple of times, and I've given this lecture a few times in the past. And I have a complete slide deck here, which I could present to you that would go straight through this outline I showed on the slide. But I also notice that these are unusual times, to say the least, and we all find ourselves stuck in front of our computers rather than inside of a lecture hall. And moreover, for the topic of this lecture, it turns out that there are some pretty cool tools available online for exploring this whole translation process, for seeing how does C code turn into LLVM IR and then turn into assembly code. And so this time around, I want to do something a bit different. And rather than just give you a slide presentation, I want to run most of this lecture in a tutorial fashion where we'll be using this Compiler Explorer tool, which is freely available on the web to all of you, to explore how different pieces of C code get translated by this process. And I invite all of you to open up your web browsers and go and load up this tool yourself and follow along as we look at this translation process. This is a fairly terrifying thing to do as a lecturer because I will be coding on the fly and invariably making some mistakes. But nevertheless, hopefully it should be fun. Sound good? I can't actually hear your responses over Zoom, so I'll assume you're all expressing agreement. All right, so let's exit that share and let me adjust the screen sharing to share a different window. And I'll start off by showing you how we're going to set up this Compiler Explorer tool for our purposes today. Okay, so you should now all see a Chrome browser window in incognito mode. So to get to the Compiler Explorer tool, we're going to browse to the website godbolt.org. Godbolt is not actually the name of the tool. That's actually the last name of the author of the tool. And by the way, objectively speaking, Godbolt is a really awesome last name. Just take a moment to appreciate how awesome the last name Godbolt is. But in any case, when you go here for the very first time, you'll see this privacy policy. It's fairly innocuous, and most of it is pretty much irrelevant for our purposes because we're not going to be entering any sensitive information into the Compiler Explorer today. But regardless, if you're at all concerned about the privacy policy on the Compiler Explorer, it turns out that you can set up this tool and run it locally on your own system. I won't go through the instructions on how you do that, except to say that what you can do is, if you're at godbolt.org, go to Other, click on Source on GitHub, and there you'll get to the GitHub page with the source code of the Compiler Explorer tool, as well as extensive documentation on how to set up that tool on your own system. But for today, we'll just be using Godbolt directly through the browser. Okay. So hopefully you've all had a chance to load up godbolt.org. And now what we're going to do is just configure the tool for today's lesson. The first thing that we need to do is set the source language and make sure that's set to C instead of C++. It turns out that when you change the language, that changes other settings in the Compiler Explorer tool. So we want to do that first. We're then going to select the compiler that we're going to be using. And for this lecture, I'm going to use the Clang 10.0.1 compiler. This isn't exactly the same as the compiler that you're using in the class, but it is very, very similar. The differences are very minor. And this generates pretty clean looking LLVM-IR and assembly, which is easy to read and reason about. Now what we see by default in the Compiler Explorer is the C code in the panel on the left and the assembly output on the right. And there are a couple things we're going to tweak for this assembly output. First of all, this is currently an Intel assembly syntax. And for our purposes, we wanted an AT&T syntax. So we're just going to click Output, the little gear thing here, and deselect the Intel ASM syntax checkbox. And now it's an AT&T syntax. Another cool thing about the Compiler Explorer is that you can actually use it to show you the LLVM-IR output. And to do that, what we're going to do is just click the plus symbol here and then select IR output. And that gives us a new panel with the LLVM-IR output for the C code. And I'm just going to position this panel, let's say right here, so that we can read both the C code and the assembly code. We'll be focusing on sort of two of these panels at a time, if you will. And the very last thing that I want to do as part of this setup is to enter in, just turn on a little bit of compiler optimization, just 01. And the reason for that is it's going to keep the assembly output and the LLVM-IR output just a little bit cleaner and easier to reason about, since this is, I imagine for many of you, an introduction into LLVM-IR and reasoning about whole functions in assembly at a time. All right. So that's how we configure godbolt.org. In case anyone got lost, I'm going to grab a link to this particular configuration of the tool, and I'm just going to go ahead and post this in the Slack. So if necessary, let me find the Slack here. So if anything went awry in that process, you should just be able to follow that link and get something that looks just like what you see on the screen. Is that good? Any issues so far? Can everyone see the screen and see the Compiler Explorer tool and hopefully have it loaded up if you wish to follow along? Okay. I'm going to go ahead and proceed, and I imagine that the TAs and course staff are on standby to give you any assistance if any issues come up. But let's go ahead and dive right into this. So what we see here right off the bat is that the Compiler Explorer tool is showing us C source code on the left and the output of the compiler in the panels on the right, where in this panel we have the LLVM-IR output, and in this panel we have the assembly output. And I want to start by looking at the LLVM-IR output. And just from the view at 30,000 feet, when we look at this LLVM-IR output, we see that it is similar to assembly in a couple of ways. For example, the LLVM-IR has primitive instructions throughout, and each instruction basically occupies one line of the LLVM-IR output. For example, we have this mul instruction on line 4 right here, and then we have a return instruction on line 5. And that's kind of like what's going on in assembly, in that you have these primitive instructions, one per line, and each instruction, roughly speaking, is comprised of an opcode, in this case mul for multiply, followed by a list of operands. Moreover, if we look at our operand list in LLVM-IR, we see these percent sigils all over the place, which is kind of like what you would see with assembly register names. And indeed, these names, %0 or %2, those correspond to what we think of as LLVM-IR registers. And so right off the bat, we see that there are some similarities between the LLVM-IR output and assembly code. But at the same time, we also see that the LLVM-IR has many similarities to the original C source code. For example, the whole output of LLVM-IR is partitioned into among different functions, where if you have a function in the C source code, you're going to end up with a function in the LLVM-IR. And moreover, the function itself adopts a syntax which is kind of C-like in many ways. If we look at our C source code on line 2, with this piece of default code the Compiler Explorer gave us, we see that the header identifies a function named square, which takes a single integer parameter called num and returns an integer result. And if we look closely at the LLVM-IR, what we see here is something that looks syntactically similar. We have our function named square. In parentheses, we have our parameters in the same order as in the C source code. And we have the return we have the type of the return value of square showing up on the left-hand side, or on the left of the name of the function. And in addition, the whole body of the function is in LLVM-IR is enclosed within curly braces, just like in C. So in that sense, functions in LLVM-IR look a little bit like functions in C. There is more stuff going on in this function. There's these additional keywords. The define keyword here says that this is the definition of a function. In other words, we have the body of the function available, and it's not just a declaration of a function whose body would be somewhere else. We have some additional variables like DSO local and local unnamed adder. For our purposes today, we can basically ignore these keywords. These keywords basically pertain to how the linking attributes on this function, and we don't need to worry about those for today. We have some additional attributes which are marked by this #0 thing. We have some metadata attached to the function, which we also don't need to worry about. This bang debug bang7 specifies that metadata. That metadata has to do with debugging information. Once again, we can ignore that for today's purposes. And within the function, we even see these calls to this funny function, llvm.debug.value. These are not real function calls. This is a way that LLVM, another mechanism LLVM uses to keep track of debug information for the function, to provide meaningful output in tools like GDB, for example. And for our purposes, we don't need to worry about this. Okay, so in the LLVM-IR, we have that the functions look somewhat C-like. The resemblance goes beyond that, in fact. If we take a look, we have this register 0, this %0 symbol here in LLVM-IR. And although it looks much like an assembly register, in fact, in LLVM-IR, there are an infinite number of registers. Each register is just distinguished by name. It's % followed by, well, for our examples, it's going to be followed by a number. In general, it could be an alphanumeric string, for instance. And there are no special aliasing properties between different registers. All the registers are distinct within a function. And any register that shows up in one function, if you see the same name in another function, that's a different register. And because we have an infinite number of these registers, which are all differentiated just by name, we can actually think of LLVM-IR registers much more like C function local variables. So in our square routine here, this %0, we can think of as the num variable in our C function. It's analogous to that num variable. And this %2 is like a local variable inside our LLVM-IR function, which happens to, that register happens to store the value that gets returned from the function. In addition, even the instructions in LLVM-IR are a bit simpler than what we see in assembly in the following sense. So we still have instructions that look like an opcode followed by a list of operands. But we don't have to worry about which of these operands is a destination operand. In LLVM-IR, whenever you have an instruction that produces a value that needs to be saved in some register, it's going to adopt a syntax like what's shown on line 4. So you're going to have a register name on the left-hand side of an equal statement. And on the right-hand side of the equals, you just have the LLVM-IR instruction, the opcode and operand list. And so in this case, we do a multiply on register 0 with itself, and we store the result into LLVM-IR register 2. And so whenever an LLVM-IR instruction produces a value, the syntax looks much more like an assignment operation in C code. Now, there are LLVM-IR instructions that don't produce a value in quite the same way. For example, this return instruction here just does a return operation. It doesn't need to save anything into an LLVM-IR register. And in that case, we don't end up with the left-hand side and we don't end up with the equals. Finally, types in LLVM-IR are, I think, a little bit simpler to read and reason about than types in assembly. So recall from last lecture that when you were dealing with assembly code, you had to remember that there were these suffixes appended to all of the opcodes, which would specify the data types involved in the operation. And that different registers could store values of different types and or of different sizes. And you just had to remember which registers could store what. In LLVM-IR, that's a bit more explicit. What we have is a simple type system, which is somewhat C-like in its syntax. If we look at, for example, our function header here, in LLVM-IR, we see that the single parameter to the square routine is an I32. And in this case, the I identifies this as an integer type, and 32 specifies the bit width of that integer. So this is a 32-bit integer. That's what the data type says. And that corresponds to the int type in C code. If I were to change one of these types from, say, int to long, so now the square routine is going to take in an integer as input and return a long as output. What we see in the LLVM-IR is now the return type of our square function is an I64, or a 64-bit integer. And so we can read through the LLVM-IR and see the uses of these types and they pretty clearly specify what are the types involved within the different operations. And so at that high level, we see that LLVMIR has some features in common with assembly language itself, but it's also simpler than x86-64 assembly, and it has many resemblances to C code. In that sense, it's easier to, I'd argue it's easier to read and reason about LLVMIR than assembly. We'll see more examples of different instructions and different data types as we try out some C code during today's lesson. Any questions so far, though? All right. So now I'd like to just dive right in. Now that we've gotten a high-level overview of what LLVMIR looks like, I'd like to dive right in and start taking a look at how different snippets of C code get translated into LLVMIR. Right now, we have a really simple piece of C code, which just does some simple straight line operations. But I'd like to start off with something a little bit more sophisticated, just so we can see more of what's happening within LLVMIR. And so let's go ahead and code up a really simple bit of C straight line code. So no conditionals, no loops, nothing like that. And we'll just creatively name this straight line. And we'll pass in a number x. And I'm going to just declare a couple of functions for our straight line code to use. So let's declare foo here. Let's declare bar. And we don't know what these functions do, but we're able to call them from the straight line. And all we're going to do in straight line is just return, I don't know, how about foo of x divided by 3 plus bar of x minus 2, or something like that. Okay, so now we wait patiently, and there we go. Now we have both the LLVMIR and assembly outputs for this little snippet of straight line C code. And we can take a look at how this straight line C code got translated into LLVMIR. So one of the convenient features of Compiler Explorer is that it highlights lines by color to show associations between different lines of C and those lines in LLVMIR and those lines in the assembly code. So what we see here is that our straight line C code maps to this block of instructions in the straight line function in LLVMIR. Just drag this over a little bit. And we can sit and reason through what each one of these instructions do, and from that deduce that these instructions do implement the operation in this straight line function. But because we know that the Compiler Explorer highlights things on a per line basis, we can actually just trick it to tell us a little bit more information. So that's what I'm going to do here. We have to keep the C code valid, but there's nothing stopping us from just adding some new lines to the code, and that will let the Compiler Explorer highlight more stuff for us so we can better differentiate what's going on. So now what we see in our straight line C subroutine, this return statement maps to the return instruction at the very end. That makes perfect sense. So you can't return a value until you've computed it. The next thing that we see, highlighted in purple here, is that our computation of foo of x divided by 3 maps to these two instructions on lines 4 and 5 in LLVMIR. The first instruction takes register 0, which is actually the input parameter to our straight line function, and calls a signed division on register 0 to divide it by 3. And it stores that result into register 2. We then use register 2 and pass it to the function foo, which we call on line 5. So line 5, we do a call of foo, passing in register 2, and we take the result of that call and store it in register 3. And that's it for implementing foo of x over 3. The next thing that we see in the LLVMIR are the lines associated with bar of x minus 2. Sorry, there's quickly a question in the chat. May I ask, what is register 1 doing? Right. So we'll get to the topic of where register 1 went. But at a high level, it turns out that the same counter that's used to automatically name the different registers in an LLVMIR function, that same counter is used to name what are known as basic blocks. And so register 1 is actually referring to the first basic block in this function. I'll talk more about basic blocks in a little bit when we start talking about conditionals and loops. Cool. So coming back to the straight line code, what we have is on line 6 and 7, we have the straight line code that implements bar of x minus 2. And indeed, we see that on line 6, we're going to add register 0 to the value minus 2 using this addition. The NSW flag here, that's a little bit of additional data on the addition instruction to help the compiler analysis. Essentially, that provides a guarantee that the compiler can assume this addition doesn't cause overflow when considering signed arithmetic. Doesn't produce a signed arithmetic overflow. NSW is short for no signed wrap. So yes, we add our argument register 0 to minus 2 and store the result in register 4. And that register 4 is then passed to the function bar on the next line, which we call in the next line. And we store the result of that call into register 5. The last thing that we do is add together the results of the two calls, the call to foo and the call to bar, using the addition instruction on line 8. And we can see that from the highlighting, from the fact that those two lines are highlighted in red. So we add those two results together, we store the result in register 6, and that is the value that gets returned by the return instruction on line 9. So straight line C code gets transformed into a sequence of instructions within LLVMIR. Pretty simple. Now there's one other thing that I'd like to mention when it comes to straight line code, and that has to do with operations that operate on memory, just because those tend to follow a pretty common pattern, and most code will involve memory operations at some point, so it's good to know what that pattern looks like in LLVMIR. So let's just go ahead and modify the straight line example to not take just an integer x, but let's take an array A and maybe an index into A, which we'll just call I. And for simplicity's sake, we're just going to have this function return A of I. Wait for that to compile. And now what we have is the LLVMIR for our new straight line routine. This routine now takes two arguments. We see that the first parameter to this new straight line function is a pointer argument, which is identified by its data type i32 star. Much like in C code, the way that pointer types are designated is by some underlying data type, the element type being pointed to, followed by an asterisk, which designates this as a pointer. And so register 0 is of type i32 star, pointer to 32-bit integers. And the second argument is a 64-bit integer, which corresponds to the index long I that we pass into the function. And let me use that new line trick once again, just to, sometimes this has a hiccup. See if I can trick it. Oh well, okay. Sometimes the compiler explorer runs into some issues. No worries, we can still reason through this. So what we see here is that we're going to return the value of A sub I. The return statement, or the return turns into a return instruction on line 7 here. We can go ahead and ignore that. The relevant part I wanted to mention was the actual memory access and what that looks like. Because in general, whenever you access memory in LLVMIR, that turns into a sequence of operations involving an address calculation followed by a load or a store, depending on whether you're reading that memory or writing to that memory. And so what we see here is that when we access A sub I, we first have this funny instruction, get element pointer, which operates on the two operands, the two parameters that we pass to this function. And then we use the return value of get element pointer, and we treat that as an address, and we load from that address on the very next line. Now it's worth talking a little bit more about this getElementPointer instruction. This is a special instruction in LLVMIR, specifically for doing address calculations. And the way that this instruction works is that it takes a list of operands where the first operand is a pointer to some memory location. In this case, that pointer corresponds to the parameter, the first parameter of a function, which is the array A. And the subsequent operands after that pointer argument are indices to that memory location. So we take our pointer to A, followed by the index 1. And this will compute the address of the index in register 1. And this will compute the address resulting from taking the pointer in register 0 and adding register 1 to it using pointer arithmetic. So for example, if I change this from A sub I to A sub 1, just as a little easier to talk about, what this address would give me would be the address in register 0 plus 1 times the size of the underlying data type being pointed to. Now the underlying data type in this case is a 32-bit integer, and so when we add 1 to it, we end up at a memory address which is 32 bits or 4 bytes away from the address in register 0. So getElementPointer is doing pointer arithmetic to compute an address, much like how pointer arithmetic works in C code. So that's what I wanted to say about memory accesses, and we'll see some more examples of this in more elaborate examples of C code. I'd like to now turn our attention to something beyond just simple straight line code in C. And let's talk about conditionals, so if then else statements. And so to demonstrate a conditional, let's just change our function once again. I'm going to leave foo and bar here because I want to use those. But I'll create a new function called conditional. And it'll take a parameter x. And let's just, I don't know, we're coming up with pseudocode on the fly, so it doesn't really matter. Let's say if x is odd, then call the function foo on x. We don't know what foo does, so maybe this is a good idea. Otherwise, call the function bar on x. And finally, return something. How about like x plus 2? Doesn't really matter. And so we wait for a second for this thing to compile. There we go. Okay. So we have the LLVMIR output and the assembly output for this function. We're just going to focus on the LLVMIR output for the time being. And in order to do that, I'm just going to drag this panel down and basically minimize it. So what we see here is that our conditional function turns into a function in LLVMIR. And in that function, we have a bunch of instructions, just like we saw before. But now those instructions have been broken up into these chunks. And those chunks are known as basic blocks. So a basic block in LLVMIR is a sequence of instructions. In other words, you can think of it as straight line code. And these basic blocks have the property that control can only enter a basic block from the very beginning, from the first instruction in the basic block. And control will flow straight through the basic block until it hits the end of the basic block. And the last instruction in the basic block, the terminator of the basic block, specifies where control can go at the end of the basic block. Now, in some cases, like basic block 8 here, each of these basic blocks is identified with a label, except for the first one, which is implicitly labeled. In this case, it's labeled 1. So if we take a look at basic block 8 here, identified by the label 8, we see that it's terminated by the return instruction, which just means we're done with this function, return control back to the caller. And occasionally you will see that in functions. In fact, you should see one of those basic blocks in each function you write. But most of the time, when you're looking at the basic blocks within a function, those basic blocks will typically be terminated by some kind of branch instruction, which is identified with this BR opcode. And there are two kinds of branches, conditional and unconditional branches. A conditional branch, as shown on line 6, has 3 different operands. There is the first operand is a 1-bit integer or Boolean value, and that specifies, and that's the predicate of the conditional branch. If that predicate is true, then control will flow then this conditional branch will direct control to flow to the true destination, which is identified by the second operand, which is given as label and then the name of a basic block. So in this case, label 6 means if the predicate is true, then this basic block will branch to basic block 6. If the predicate is false, then control will branch instead to the second label in our operand list. In this case, that's label 4. So if the predicate is true, we branch to label 6, and if the predicate is false, we branch to label 4. That's what a conditional branch looks like in LLVM-IR. There are also unconditional branches in LLVM-IR, and those are simply branch instructions with a single argument, and that single argument identifies the basic block where control can flow to next. And so at the end of both basic blocks 4 and 6, we have an unconditional branch to label 8, meaning basic block 8. And so what we can do is squint at this code and reason about each of the pieces of straight line code and confirm to ourselves that in fact this LLVM-IR code does implement the C code that we show on the left, and the highlighting in the Compiler Explorer can help us do that. The other thing that we can do, if we squint at this code long enough and think really hard about it, we have these blocks of straight line code, these basic blocks in the function, and we have these branch instructions that will direct control flow here or there from one basic block to another. And if we think hard about that, we can kind of see that these basic blocks actually form a graph known as a control flow graph, where each node of that graph is a basic block, and the edges of that graph describe how control can flow from one basic block to another. Now, staring at flat text like LLVM-IR and thinking really hard about how that flat text translates into some kind of control flow graph is technically possible, but I confess is not my favorite hobby. Unfortunately, the Compiler Explorer doesn't give us a great way to look at control flow graphs for the LLVM-IR itself, but you should have access to a tool that would let you do that available on your systems. And I'll just briefly show you that tool in action. Before I do that, I'm going to copy the code of this conditional function we wrote. And I'm just going to switch my share over to a different screen. Okay, so now you should see just a terminal. And what I'm going to do here is just open up a file, conditional.c, just set up as an empty file. I'll paste the code that I wrote in the Compiler Explorer, save that file, and then what I'm going to use, what I'm going to do is compile this down to LLVM-IR using Clang, and because this is in my history, I can just go ahead and search it, conditional.c, and I'm just going to use the flags -s, -emit LLVM, and the same level of optimization we were using before to compile this conditional code. That's going to produce an LLVM-IR file, conditional.ll. And now what I'm going to use is this tool called opt. And opt is capable of doing lots of things, but for today's purpose, all I'm going to do with opt is ask it to give me a pretty picture of the control flow graph for this code. And I'll do that by saying -.-cfg, -cfg. And in order to prevent some warnings, I'm just going to say disable output for opt. And that writes the graph into this file .conditional.dot. And now I can use the dot program to translate this dot file into a pretty picture, and I'll ask it to give it to me in the form of a PDF. That should be good. And now if we go ahead and open this PDF, we get a pretty picture of the control flow graph for this function. And so what we see here is that each of these nodes is a basic block. Each basic block starts off with the label of the basic block. In this case, we see our %1 showing up here, as well as 6, 4, and 8 for the other basic blocks. And the edges connecting the basic blocks describe how control can flow between the basic blocks, as I described before. And in general, whenever you have an if-then-else statement, that gets transformed into this high-level diamond pattern in the control flow graph. Cool. Can you make the diagram bigger, please?
Make the diagram bigger.
Absolutely. Let's go over here and how's that? So hopefully you can all see the control flow graph, and you can see that inside each basic block we have our same LLVM-IR instructions. It's not as pretty as what we get out of the Compiler Explorer, but it can serve us pretty well. And so we can see this diamond pattern from our if-then-else statement in the conditional function. Cool. All right. Let's go back to the Compiler Explorer and take a look at some other examples of C code. Let me just switch the share back. Right, there we go. Hopefully that's the right window. All right. So now you should see the Compiler Explorer once again. So that's what conditionals look like in LLVM-IR and how they produce a control flow graph by dividing the code into basic blocks and having branch instructions, for example, create these control flow edges between basic blocks. Now, I want to pose a bit of a puzzle to you, which does arise specifically in LLVM-IR. And in order to pose this puzzle to you, I need to tell you about one key invariant that's maintained by LLVM-IR. And that invariant is known as static single assignment. LLVM-IR maintains what's called static single assignment form, which basically means that for any given LLVM-IR register within a function, there is at most one instruction within the function where that register shows up on the left-hand side of an equals. So we see here in our conditional function that there's one place where register 5 is on the left-hand side of this equals, and there's one place where register 7 is on the left-hand side of this equals. And there could be and one place where register 2 shows up on the left side of this equals. And there could be other uses of this register throughout the code, but all other places where register 2 is going to show up is going to be in the operand list. So statically, meaning in terms of the code, there is a single place where the register is assigned, static single assignment. This turns out to be a really handy invariant from the compiler's perspective for reasoning about the code and thereby being able to optimize the code, but it does present a bit of conundrum. For example, suppose that I have in my C code some variable that adopts a different value depending on how control flows through that program. Well, in terms of LLVM-IR registers, depending on control flow, I might be assigning to different register values, and I have to maintain this static single assignment form. So when we reach a point in the code, like after a conditional statement, where I want to query what is the value of this C variable, it's not clear exactly how I refer to the correct value, to the correct LLVM-IR register, because it depends on control flow. So how does LLVM deal with this problem? Well, let's just try it out and take a look. So I'm going to go ahead and modify this conditional function to declare a new variable y. And here, I'll set y equal to the result of foo of x. and here y equal to the result of bar of x. And just to make sure that this variable y is actually used, I'm going to go ahead and return it from the function. And now we wait patiently for the compiler explorer to compile the code. Ah, that's a shame. Sometimes you can jog it just by moving things around. Let's see. Yeah. All software has bugs, including this tool. But in any case, we can find ways to resolve those bugs. And that's what we've done here. Okay, so we now have the LLVMIR output for this C code, as shown in this panel. And we can take a look at how LLVM has resolved this conundrum. Because what we have here is a variable whose value is set either to the return value of foo or the return value of bar, depending on control flow. And then we want to return that value y in the final basic block. If we take a look at our LLVMIR function, foo and bar will return their values into different registers. And so what we get in the final basic block to specify which value to return is this special instruction called a fee instruction on this line here. This is basically a quirk of LLVMIR to maintain static single assignment form. But I'll walk you through what this fee instruction means. The fee instruction specifies that the result of the fee should adopt a different value depending on which predecessor basic block executed immediately before this one. So let's look at this specific fee instruction as an example. Each of the operands of the fee is a pair where we have square braces designating that pair. And we have one pair of values for each predecessor basic block. So this pair, what this says is that if control came from basic block 4, and that's how it reached basic block 8, then the result of this fee instruction is going to be the value in register 5. Meanwhile, this pair, 7, 6, says if instead control came from basic block 6, and that's how it reached basic block 8, then the result of this fee instruction is going to be the value in register 7. And so this fee instruction captures the correct register value depending on which predecessor basic block executed immediately prior. And it stores that into a single register, which we can use in subsequent instructions, such as this return instruction here. So like I said before, this fee instruction is just a quirk of LLVMIR, and it's important to note that a fee instruction doesn't necessarily correspond to a real instruction in the assembly language. It's just there to maintain this static single assignment form. Okay, let's look at one more example snippet of C code and see how that gets translated into LLVMIR. And this time, we're going to take a look at a loop. So let's delete this function that we had before. And let's just create a really simple loop. I'll call it DAX. And we'll give it an array y for output, a scalar double value a, an array x for input, and the size of those two arrays, which I'll specify in this variable n. And then inside this function, all we're going to do is say for I equals 0 up to n, incrementing by 1, set y of I equal to a times x of I. And now we wait patiently, and we don't have to be that patient this time. Here's the LLVMIR output. I'll shrink this down a little bit more. So what we have here, once again, the for loop is a bit of implement some complex control flow in our C program. And once again, what we see is that our function is divided up into these chunks called basic blocks, where we have our entry basic block of the function, which actually just does a simple test to see if n itself is bigger than 0. In other words, if there are any iterations of this loop to execute. And then we'll either branch straight to the return if there's nothing to do in this function, or it'll branch to this basic block here. And this is where all the really all the content of the loop exists. And the highlighting facilities in Compiler Explorer let us break down the contents of this loop. What we see here is that we've got some content that corresponds to the body of the loop, the actual computation of y of I equals a times x of I. And that maps to some address calculations. We see a get element pointer followed by a load, and then a floating point multiply operation, and then another address calculation, get element pointer, followed by a store. And so this straight line C code in the loop body turns into a sequence of instructions in this basic block. And the rest of the instructions in the basic block correspond to the loop control. And to break that down, we're once again going to trick the highlighting facilities in Compiler Explorer just by inserting some innocuous new lines. So it'll highlight more stuff for us. So what we see here is that the loop control, which involves this induction variable, some initial value of the induction variable, a comparison, and an increment statement, get mapped to a few different instructions within the LLVM-IR. We see that the comparison shows up a couple of times. This line 6 maps both to the initial comparison in the function, as well as this comparison in basic block 7. If we look at this comparison, we see that it actually operates on register 13, which was assigned on this line here, and that actually corresponds to the increment of our induction variable I. And then finally, we have a conditional branch, which will either take us to this basic block from which we return, or back to this initial basic block, or back to the beginning of basic block 7. And so this is kind of interesting. What we have here is that we have a branch instruction that could take us to a different basic block or back to the beginning of the same basic block. And so if we think about what this looks like in terms of a control flow graph, what we see is that the control flow graph itself actually contains a loop whenever we have a loop in the C source code. And we can see a quick example of that, once again, by using the opt tool. So let me just switch the share back over to the screen. You should now be able to see the control flow graph from before. And I'm just going to do the same process as before to use opt to generate a pretty picture for us, pasting the code of this function that we just wrote. Yes, go ahead and save it. And then we'll use Clang to compile this code. -s -mid LVM -01, that's fine. We'll then use the opt tool to generate a pretty graph. We'll then use the dot tool to make that pretty graph into a PDF file. And if I didn't typo anything too badly, voila, there is our control flow graph for the loop. And indeed, we see that we have an entry block, this return block, and for our very simple loop, we have an edge that goes from the end of the loop, or goes from the end of the basic block, back to the beginning of the basic block. So indeed, our control flow graph itself contains a loop. So a loop in C code gives us a loop in the control flow graph. Now, the last thing I'd like to point out when it comes to the C code has to do with the induction variable. I'm going to go back to the Compiler Explorer for this part. Okay, so now you should be able to see the Compiler Explorer once again. And what we see here, if we trace through the C code, or sorry, if we look through the LLVM-IR, we have this variable I in our C code, which gets, it's used to control the execution of the loop. It's used for index calculations for y of I and x of I, but it's also incremented and compared against the value of n. And because LLVM maintains this SSA form, it turns out that we can't store the induction variable in LLVM-IR in just a single LLVM-IR register. Instead, it ends up getting distributed across a couple of different registers. So let's see how that works. Well, this basic block 7 actually has a couple of predecessors. There's the entry block of the function, as well as basic block 7, since we can loop back around to the beginning of this basic block. And so we end up with a phi node, with a phi instruction at the beginning of the basic block, which specifies if we came from the entry of this function, then the return value of the phi instruction is going to be 0. So that's the initialization of our induction variable. And if instead we followed this back edge, as it's called, around to the beginning of this loop, then we're going to adopt this other register value 13. And that's going to end up in register 8. And we can see that register 8 gets used in a couple of places. It gets used in this get element pointer instruction as an index, which makes sense because we're using I to index both the Y and X arrays. And then it's used again in this addition operation where we add 1 to it. So that corresponds to incrementing the induction variable. Because we have SSA form and LLVM, the result of that add ends up in register 13. And then we use register 13 to perform the comparison to see whether or not we should exit this loop. And if we don't exit the loop, that register 13 is consumed separately by the phi instruction at the beginning. So although we have a single induction variable in our C code, it gets translated into multiple LLVM IR registers because of this SSA form on loops. Now, the last thing I'd like to point out about LLVM IR is that there's a bunch of other information packed into the LLVM IR, and a lot of this information has to do with attributes. And these attributes pertain to, or they specify a little bit of extra information about the different operations. So for example, if we take a look at these load instructions, we see that there's this extra information in the form of align 8. And that's an alignment attribute that specifies that this load instruction, or rather this separately the store instruction, is always going to operate on memory that is 8-byte aligned. So align 8 means 8-byte alignment. We can see other attributes throughout the LLVM IR as well. Specifically, if we look at the parameters of our DAX function, we see that the compiler has actually decorated some of these pointers with a couple of attributes. There's this no capture attribute, which pertains to what the compiler understands of how other functions may operate on this pointer, or how this function allows other functions to access this pointer. And we also see this read-only attribute on the third parameter of the function, which corresponds to the pointer to X. And so what we see here is that the compiler has actually figured out that the array X is only ever read from. It's never written to. And it maintains that information by decorating this pointer with the read-only attribute. Now there's some other attributes that can show up in the LLVM IR code due to how we write the code. So for example, if we modified our DAX routine to specify that actually the X and Y pointers never alias, and in other words, if we add the restrict keyword to these pointers, we have to type correctly in order to do that. All right, so if we add the restrict keyword to these pointers, now when we take a look at the parameters of our function, we see that they have this additional no alias attribute, which corresponds directly to that restrict keyword in our C code. So we'll find these attributes throughout LLVM IR, and some of them are derived from compiler analysis, and others come from attributes that we specify directly in the C code itself. And so that's a bit of a whirlwind tour of LLVM IR and how different C structures and constructs get translated into LLVM IR. Any questions on that so far? Okay. So in order to finish the story of how C gets translated all the way down to assembly, we've now seen how it gets translated to LLVM IR. So now we have to translate that code back into assembly. Now there's a bit of good news. After translating C into LLVM IR, the compiler has solved one of the key problems that we mentioned before. pertaining to the LLVM-IR. Namely, it's figured out how to implement various constructs like loops and conditionals in C code using conditional and unconditional branches. It's largely solved the structural problem of how to structure the code into basic blocks when it translates it into LLVM-IR. And we can kind of see that because the Compiler Explorer will let us view the CFG corresponding to the assembly output, not to the LLVM-IR output, but at least to the assembly output. And so if we add new graph output in our Compiler Explorer, we actually get a graphical representation of the control flow graph for the assembly output, in this case for our loop. And if we look at this control flow graph, we can see that it's not exactly the same as the control flow graph that we got for the LLVM-IR, but it's pretty close. We still have this basic block, which contains the body of the loop, and it still contains this back edge. And we still have this basic block where the entry or the loop can go to just to return from the function. So a lot of the structural problem for translating C code to assembly has been solved by the time we translate it to LLVM-IR. So that means there's just a few things left for the compiler to do. Well, there's still a fair amount left for the compiler to do, honestly. What does the compiler have to do? Well, it still has to select which assembly instructions it's going to use to implement different instructions in LLVM-IR. It still has to choose how to allocate registers in order to hold different values. After all, assembly code doesn't have an infinite number of registers. And it has to figure out how to coordinate function calls. And it turns out that coordinating function calls is one of the main sources of complexity when it comes to translating LLVM-IR to assembly. And so that's going to be our focus for the last part of this translation process. So I'm going to switch back to the slides. Assuming that's possible. All right. So you should now see the slides. And since we're focusing on that translation process, that brings us to the topic of the calling convention, which is used to coordinate these function calls. So to talk about the calling convention, there we go. Okay, to talk about the calling convention, we need to remember exactly how is a program laid out in memory at runtime when you actually execute the program. How is it laid out in virtual memory? Well, to execute a program, virtual memory gets organized into these different regions known as segments. There's one segment that contains the code of the program itself. That's known as the text segment. There are a couple of segments to store static information. There's the data segment for storing initialized data and the BSS segment for storing data initialized to 0. And then there are a couple of segments for storing dynamically allocated memory. There's the heap segment, which grows upwards in virtual memory. And there's the stack segment, which grows downward from the top of the virtual address space. And on modern machines, we basically rely on the fact that although the heap and the stack segments seem to be growing towards each other, virtual memory is gigantic on modern machines. And practically speaking, these two segments simply never meet. Now, if you look at assembly code that you generate directly from the compiler or that you get from using the object dump tool, you'll actually see references to some of these segments within the assembly file in the form of segment directives. These are annotations like .text or .bss or .data, which will organize the content of the assembly file into these different segments and specify how that assembly file needs to be placed in virtual memory at runtime. You may also discover other directives in the assembly file, for example, storage directives for allocating space or storing constants or for implementing alignment at various places. And you might find directives for scope and linkage, like the .global directive, which specifies that a label is visible to other object files in the system, meaning that those other functions that were separately compiled could call this function fib in this case. But let's get back to talking about these different segments. And in particular, I want to focus on this segment, the stack segment at the top of virtual memory. Because this stack segment is used to implement the call stack. It's used to manage memory in order to coordinate function calls and returns. Now, hopefully you've seen some discussion of the stack segment in previous classes, such as 6004. So who can remind me, just by typing in the Slack, what kind of data ends up being stored in the stack segment? What do we need to store in the stack segment in order to manage function calls and returns? Yep, the return address, that's one. Local variables, perfect. Anything else? Caller static variables. I'm not quite sure what you mean by that. So both of these are good. And indeed, in order to manage function calls and returns, whoops, let me get back to the slides. To manage function calls and returns, we have to store the return address, like you identified. We have to store function arguments and local variables that don't necessarily fit within registers. And we also have to store some amount of register state. After all, the functions in assembly are all using the same set of general purpose registers. And we don't want those functions to clobber over each other's register state. And so occasionally, whenever one function calls another, it will save some of its registers onto the stack, and then it can pick up those values off the stack once that function, once that called function returns. Okay. Now, if you think for a little bit about how might functions use this stack space in order to store register state and function arguments and so on, you can come up with a lot of different creative ways for storing all this information. But there's this fundamental problem. You might even come up with creative ways that only work for specific functions but are really efficient. But there's this problem that, in general, programs involve a lot of different object files that all get linked together. And you may have some object files in that set, such as in libraries, which were compiled by different compilers at different points in time. And there was no way that those libraries could know that you have some special way of managing the call stack for calling a function in one of your object files. And so there's this problem of how do we make sure that function calls and returns amongst all of these separately compiled object files are all properly coordinated and that they all use the stack in a consistent way? Well, the answer is that we force the functions to abide by what's called a calling convention. And there are a bunch of different calling conventions. They vary depending on operating systems and instruction set architectures. We'll focus on the calling convention that comes up in this class, which is the Linux x86-64 calling convention. And what this calling convention does is it organizes the entire stack segment into sections called frames, where every single time a function gets called, that function instantiation is going to get its own frame. In general, the calling convention uses two pointers to maintain the frame of any function instantiation. There's the base pointer, also known as the frame pointer, RBP, which will point to the top of the currently executing stack frame. And there's the stack pointer, RSP, which points to the bottom of the stack frame. Now, when the assembly code itself executes call and return instructions, those instructions will use the stack as well as the instruction pointer RIP in order to manage the return address of each function call. So for example, when we execute a call instruction to call a function A, that call instruction will take the current value of RIP and push it onto the stack, and then jump to the specified operand A, which is a label in the assembly code, and that specifies the address of the function. And the return instruction does the opposite. It pops the address RIP off of the stack, and then uses that as the address to execute next, thereby returning control back to the caller. See, there's a question in Slack. Why do we need 2 pointers for the stack if the size of the stack frame is known statically? Great question. Your question will be answered in a few slides. But really good question. Okay, so the call and return instructions will manage the return address as described previously. We have this other problem that we need to maintain register state across function calls. And if we think about how to solve this problem, there are a couple of possible solutions. One option would be to have the function that's doing the call, in other words, the caller, save any registers that it's using onto the stack before performing the call. The downside of this approach is that the caller might waste work saving that register state if the function that it is calling doesn't actually use those registers. So that could be inefficient. We could flip the script on this and instead say, okay, let's have the function being called, in other words, the callee, save the state of any registers that it wants to use. But this has the opposite problem. If the caller wasn't using a particular register, then the callee might waste work saving register state that the caller wasn't using. So we have these two approaches, and they have symmetric problems. What do we do? What do we do in this case? Which approach do we adopt? Any guesses in the Slack? Both. Perfect. We do a little bit of both. That's exactly what this calling convention does. It identifies some of the general purpose registers and designates them as callee saved registers. And all other registers in the system are caller saved. Excellent. Now, to summarize how the different registers are used in this calling convention, we have this handy table here, which is an extension of the table you saw in the last lecture, which describes all of the general purpose registers in x86-64, but it also describes their C linkage. In other words, how they're used for function calls and returns. So the RAX register is used as a return value. There's some registers like RDI and RSI and RDX, which are used to store the first, second, third argument, so on and so forth, given to a function. There's the base and stack pointers, which we already talked about, and there are a bunch of callee saved registers as well. In addition, whenever you've got a function that deals with floating point arguments, floating point values cannot be stored in these general purpose registers, and the calling convention specifies that it will use the SSE registers XMM 0 through 7 in order to pass around floating point arguments. Okay, so let's take a look at, in order to describe this calling convention sort of in full, let's take a look at a worked example. And in this setup, what we have here, what we're going to see is what happens when we have some function B, which was called by some other function A, and is about to call a function C. So because we have this function B, which was called from function A, at this point in time, we have on the stack segment in virtual memory some content corresponding to B's stack frame. And B's stack frame is organized as follows. At the top of the stack frame, there is a linkage block, which stores non-register arguments that the function A passed to B. And the function B is able to access any of those non-register arguments off of the base pointer RBP using positive offsets. Recall that the stack in this case grows downwards. After the linkage block, we see that we have the return address of A as well as the base pointer for A before it. And then we get a region of the stack segment for storing local variables for the function B. And B can access these local variables by indexing off the base pointer with negative offsets. And finally, at the bottom of B's frame, we have yet another linkage block, which is going to be used to store non-register arguments that the function B will pass to any of its callees. For example, the function C. And once again, we can access these locations using negative offsets. So what happens when B actually calls C? Well, the very first thing is that before calling C, the function B is going to place those non-register arguments into this linkage block, which it's going to share with the function C. Then it's going to go ahead and execute this call instruction to call the function C. And that's going to push the return address onto the stack before transferring control to the function C. Once it transfers control to C, the first thing that function C does is it executes what's called a function prolog, which consists of the following. First, it's going to push the current value of the base pointer RBP onto the stack, just like that. It's then going to set the base pointer equal to the stack pointer, thereby setting up the base pointer for C's stack frame. And then it's going to advance the stack pointer. Recall once again that the stack grows down in order to allocate space for local variables that C will use, as well as any arguments, as well as a linkage block that C will use for any of its callees at the very bottom. So that's how a function call works. We store the return address, and then we update the stack as illustrated. Now, coming back to that question in the Slack, what if you know that a function never actually does any stack allocations except as necessary for function calls and returns? In that case, the difference between these base and stack pointers is actually a compile time constant. And so to answer the question of why do we need two pointers, the answer is we don't. And the compiler, when it recognizes this case, can be very clever and say, let's not even bother maintaining the base pointer for this function. Instead, we'll just do all indexing into the frame using positive indices off of RSP. And that allows it to reuse RBP as an ordinary general purpose callee save register. Now, there's actually a lot more to the C calling convention, which I didn't get to cover today. All of that is documented in the System 5 ABI, which I believe is among the course notes for this class.